Welcome to day 4 of the 2021 summer series. Today we have 2 programming workshops, the first of which will be done by Brendan and I, where we'll be doing Java programming in FRC. And after the break at 5:50, we'll hear from the super nerds about making a state-based autonomous program. Stay tuned for that. And without further ado, please go ahead, Brendan.
All right, so hello everyone. This is the Robot Dolphin Summer Series workshop on FRC Java programming. My name is Brendan Area, and I am presenting with my Team Spider teammate, Marshall Hammond.
Going into our 17th year, Team Spider, number 1622, is the robotics team that represents the Poway High School Engineering Academy. We build and program robots to compete in competitions such as FRC and VEX. But we're so much more than that. As members, Team Spider members also get to be part of a real business environment and be involved in our community, from various local government meetings. Our goal is to get involved and help others get involved in STEM, science, technology, engineering, mathematics, and we travel to events around the world, connect with experts and professionals, and build sustainable relationships and opportunities to make this happen.
So by the end of this presentation, you will have a better understanding of Java programming, especially in FRC. And this includes the basic ideas behind interfacing with motors, using sensors, visualizing before programming. We'll briefly go over autonomous routines. We'll go over Gamepad inputs, and we'll also go over the FRC softwares necessary to run an FRC robot using Java code. These include the WPI library as well as the driver station, and there'll be time to answer any questions at the end.
In order to execute code on your robot, you need to define the code, deploy it to your robot, and then execute it. VS Code with a WPI extension allows for both the editing of the source directly and deploying of the source to the robot. And the FRC Driver Station allows for a programmer or driver to interface with the code that is currently on the robot. Guides to install these software are shown on the screen and will be posted in the chat now.
Yeah, so if you could post those links into the live chat, that'd be great.
Are they posted yet?
Yep, it looks like it.
All right. The most popular programming paradigm is object-oriented, and it is what we will be using for FRC programming, whether you use Java, C++, or to a lesser extent LabVIEW. The main premise of the object-oriented programming paradigm is the idea that real-world things can be modeled with details about some of their attributes and some of their behaviors. Classes are the template for which objects are built. For example, the blueprint for a car. All classes have ways to define their parameters, constructors, attributes, member variables, and actions, methods, if you will, that either modify some internal state, return a value, or both. Objects are the individual cars themselves, such as a car of a specific model, a specific license plate, a specific color, etc.
All right, I wanted to go over just an example of something that we can implement onto the robot using code. So here's an example. It's interfacing with motors. So the simplest way to get a motor running is to assign it a set fraction of that motor's maximum voltage using the .set method. So .set -1 would reverse the motor using as much power as possible. .set 1 would power the motor forward with as much voltage as possible. And as you might imagine, .set 0 would stop powering the motor. So decimals between -1 and 1 would power the motor accordingly. So the .set method allows us to very easily put as much power into the motor as possible. But at the same time, if you wanted precise movements, this would be the worst option because it relies on the motor's maximum possible voltage, which is constantly changing as the battery may not be able to give as much voltage to that motor. As you can see down at the bottom, there's some example code. Right here, I can see that the left motors would be going at 0.5 speed, while the right motors would be going at -0.5 speed. So by this logic, it will spin the robot clockwise at half speed. But if for whatever reason, the left motors, let's say, are not getting as much power from the robot's battery, then the left motors will not be turning at the same speed as the right motors, just because the .set method relies on the maximum voltage, which isn't necessarily always the same. All right, so setting power, let's give a different example of a way to set power using a motor. So there's a dot set voltage method. This is a more precise way to move a motor, and this uses controlled voltage. So let's say we have dot set voltage 10. This would power a motor using exactly 10 volts. So whatever number we put inside those parentheses correlates to how many volts will power that motor. This way of powering is a lot more controlled because the number that we use doesn't sway based on the battery's voltage. So in this example, it would also spin the robot clockwise because the left motors would go forward while the right motors reverse. But now it's a lot more accurate because motors are using the exact same voltage.
Sensors. Sensors are used to get feedback from the environment the robot is in. And this is either to help the driver, such as a line light pivoting the shooter to lock onto the retroflective tape under the goal, or to help with an autonomous program be more precise. This can be done using encoders, PID control, maintaining a certain speed. Two of the more common sensors, one of the ones we have images of here, are gyroscopes and encoders, which allow for you to record angular position and velocity of one or more axes, or encoders, which are integrated with a motor controller or allow for you to track the revolutions of a shaft. Some other relevant FRC sensors can measure force, distance, brightness, and color. Now that you know about the types of sensors you may find yourself using, let's talk about how we can implement them. A motor controller with an integrated encoder that 6222 has a lot of experience with is the Spark Max, which has the built-in get position and get velocity methods. The get position methods is a double representing the amount of rotations of the shaft, and the get velocity methods returns the rate at which the shaft turns. Types of gyroscopes that we use are such as the ADXRS 450, which was also brought up in the previous slide. It is compact and simple with a simple get angle method to return the current heading. A more advanced gyroscope, such as the NavX, has a lot of utilities, from an accelerometer to being able to measure temperature to pressure to even being able to detect magnetic fields. But the three relevant methods for getting the position of its three axes are the get yaw, get pitch, and get roll methods, which return the yaw, pitch, and roll, respectively.
All right, so oftentimes it's better to use pseudocode or flowcharts before diving into a program and programming all of that out. And that's just so it's easier to visualize and correct flaws before fully committing to an idea. So now to explain what pseudocode and flowcharts are, pseudocode is plain text. It lays out a rough blueprint of what the actual program would look like, but there's no syntax or rule. Nothing reads pseudocode, it's just a rough draft for the programmer. Now, flowcharts are a lot more visual and help find a good structure for a program. It uses arrows to point to the next little bubble of instructions that give short descriptions of what the code would do if it was actually fully written out. And there are a lot of examples on the next slide. All right, so on the left, you can see an example of pseudocode. And if you compare that to the flowchart on the right, you can see that they're trying to accomplish the same thing. Both of them are trying to rotate and aim a shooter mechanism. There's no right or wrong way of doing either of these. There's no right or wrong way of writing pseudocode or making a flowchart. But I would really recommend doing this before diving into programming and kind of basing how you program off of the pseudocode and flowchart that you've laid out. Because it makes the whole process a lot less complicated if you already have a working structure in mind. For the flowchart, I use draw.io, which can be linked to your Google Drive so that you can just create a flowchart right from Google Drive. Or you can go straight to draw.io to create a flowchart. And that'd be awesome if we could put that into the chat as well, a link to that. Or I guess you could just search up draw.io. That would work as well.
From a programming perspective, an FRC game has two periods: a period where the driver control is present and a period where the robot must get along with its own code and sensors for that matter. I don't really want to touch on autonomous to a greater extent than these basic concepts, as the talk immediately after us is based on state-based autonomous control. But just know that there's more to programming a robot than teleop control, and the challenge of autonomous comes from creating and optimizing code while implementing sensors and carefully calibrated values that are derived from tools or from trial and error.
Since there's no driver input during the autonomous phase, the autonomous program has to be really smart, as one miscalculation puts the robot off its path for the rest of the game. So this is why sensors are imperative at this point in the competition. Something to keep in mind for autonomous is that usually tasks are worth more points. So strategies like collecting all the balls so that you can score a bunch of points come the teleoperated period are not all that great compared to autonomous routines that can score points autonomously. So that is just something to keep in mind when you're making an autonomous strategy. Now, the first thing that you want to do before even getting started with writing code is laying out that strategy for the entire period. And when you do this, you really need to keep in mind all of the game rules and read over the game manual as many times as you can, because oftentimes teams plan out their autonomous routine and spend hours programming and debugging only to find out that their autonomous routine goes against a rule. And when that happens, you pretty much have to rewrite it all, make a new strategy, and it's not very fun. So once you have laid out a good legal routine, you can start to create the autonomous program. When you're doing this, you don't want to rely on things like timers or battery level, or even like the color of light in the room. I know I've neglected this rule before, and when the battery gets a little bit low, then the motors and servo motors don't work the way they should, or the way that has been tested and proven to work, and then everything goes wrong. Or the color of the lights in the room change, then your color sensors and your cameras are giving improper data, and in match that can mess up the routine. So now we're setting the robot's position. No matter how flawless and reliable your autonomous code is, there might always be a chance for something to go wrong and put it off its path. And when this happens, it's important to reset the robot to a reliable position and rotation. So whether it be banging the robot against the wall to line it straight up, or using color sensors to know exactly where the robot is, you always want to reset the robot throughout autonomous to make sure that it doesn't go all the way off course for that entire rest of the period. And I think this makes all the difference.
Let's review the anatomy of a typical gamepad. The gamepad is the main input device that you use during the teleop period to get feedback from the drivers to control the robot. It has three main classifications of input methods, which are axes, buttons, and the D-pad. I'm going to talk about the D-pad in the next slide, but in order to interface with the axes, each axis is assigned an ID from 0 to 5, and you can use the gamepad.getRyAxis method, which will return a value from either -1 to 1 or from 0 to 1, depending on the type of the axis. The difference is that for the trigger buttons on the bottom halves of the front part of the gamepad, they're called the left throttle and right throttle, have an ID of 4 and 5. Those values go from 0 to 1, where 1 is it's fully compressed and 0 is when it's released entirely. All other axes, which make up both of the two-dimensional sets of the joysticks, are in the range of 0 to 3, and they return values from -1 to 1. In order to get whether or not a button is pressed, you can look at the lookup table for their ID as well. So for example, if you wanted to determine as to whether or not the A button was pressed, you could type in gamepad1.getRawButton of 2. Another thing that teams do is sometimes they set up enumerations or constants to make it so that you can refer to the variable name x, a, b, y, or lb, or whatever, in order to make it so that you don't have to memorize the raw value or consult a lookup table. The D-pad is a little bit different. You have a single method that controls its output, or lets you read its output, and that is the .getPOV method. This method returns the angle that the D-pad is facing in 45-degree chunks, and if the D-pad is not pressed at all, it returns -1. So, for example, if you wanted to check if the D-pad was pressing the front one and nothing else, you would check if gamepad1.getPOV == 0. If you wanted to check if it's going full reverse, gamepad1.getPOV == 180. And if you wanted to check if it was going if the top one and the right one are being pressed, you could use the example, which is gamepad1.getPOV == 45. Okay, another thing I'd like for you to take away from this talk is the two main methods to control a differential drive base. Differential drive base includes tank drive, and you're going to be talking about how you control it through pairs of joysticks. For the tank drive control method, you have each joystick's vertical position correspond to the speed of the respective half of the drivetrain. Which, if you look at the diagram here, means that if you have both sticks facing forward, the robot would move forward. If you have one forward, one backward, it would turn. If you had them both backward, it would go backwards. And of course, if you have them both at rest, it would stay at rest. The alternative is arcade drive, where you have one joystick's vertical position correspond to the linear speed of the robot, the absolute speed of the robot, and the other joystick's position correspond to the rate at which the robot rotates. So they can be integrated into either one or two joysticks. In fact, the main advantage of arcade drive is the fact that you can incorporate it into one joystick, leaving the other one occupied for some other mechanism. Otherwise, you see tank drive used more often because it gives you more direct control of the robot. But an example would be not moving the right joystick at all in this setup would have the robot move directly forward or directly backward, and only moving the right joystick would have it turn from left to right, and a combination thereof could describe any form of motion.
All right, now I want to talk about the driver station. So the driver station is the most useful piece of software that comes with the FRC game tools. And you could download it if you search up National Instruments FRC game tools. And I'm sure one of the guides, the link in the chat goes to one of the guides, and you can find it there. And that'll just take you to the download page. But once you get it, all the game tools, you'll have the driver station, and we can also put the link to that in the chat, the link to the download. All right. So the driver station is pretty much the command center for connecting to the robot. It sends the inputs for the gamepads to the robot. It shows where the code, if the code is deployed. As you can see in the image down there, there's a lot of different numbers and gadgets that are just super helpful and kind of necessary with sort of connecting to the robot. And there's a whole lot more, like there's more tabs below where you can go and see a whole lot more about the robot. So getting yourself familiar with the driver station is pretty much necessary if you want to use code on the robot. And overall, I'm glad that it tells you so much, because I've used a lot of that information before when both debugging or just during a game trying to drive the robot. It's very useful.
The FRC driver station is useful for, and it's called the driver station because it's intuitive enough that it could be used by drivers or by programmers. And from this window alone, you can see that it gives you indication as to whether or not you are connected to the robot, whether or not the robot has code deployed, and whether or not you have any attachments. It will, if you look at some of the other tabs that aren't shown here, it will also give you insight as to what ports your current gamepads are plugged into and what your robot's battery is. But now that we've talked about the driver station, we'll talk about the second most useful game tool, which is the PC dashboard. It's the other main tool you'll be using, and you can get it and learn how to install it. In fact, you install it as a bundle with the other game tools. It allows for you to receive sensor and gamepad input values, get provide direct control to the motors. As you can see, the drive motors part right there. Allows for dynamic modification of variables and even allows for you to specify programmable commands and execute them.
All right. So if this presentation has left you with any questions about things we didn't cover or we didn't explain a particular element of our presentation well enough, feel free to ask any questions. There will also be guides to setting up the WPI library, or WPI lib for short, as well as the driver station. So we can put those in the chat for you to check out. And Marshall, we might even want to go through those and present the guides. Those might be useful to walk through maybe. All right.
I'm going to now exit this presentation and show you our the WPI lib installation guide. So the website is docs.wpilib.org, and in order to access the installing the tools, you can look at the Zero to Robot installing software section. So in this section, it'll give you a list of how to install the different tools, such as the game tools and the WPI lib installation guide. The other one, which is LabVIEW for FRC, is less relevant in the sense that you only need to use it if you know how to do LabVIEW, and this is for C++ and Java. So let's look at how you can install the game tools. That was the wrong button. Here. Okay, so this will depend. So the FRC game tools contains 3 things by default, which are the LabVIEW update, the driver station, and the utilities. The utilities control includes the PC dashboard, among other things. These steps, which aren't applicable to you if you haven't had these installed yet, are to uninstall the old versions or any previous existing versions you have of the driver station and the game tools. Let's skip over that. And after that, you can try and download the .iso file from the link I believe they have provided. Yeah, here. Let's just take a look at what that would be. It's this page right here. But once you go to here, it'll give you .iso files for your Windows computer, in which you can then mount and then run them. You must accept the software agreement. So Windows Fast Startup is something you want to avoid because it would mean, it usually, let me just tell you that it leads to issues. When I installed it at first, I enabled it and I had to reinstall the entire thing. After that, you can go to the package manager installation, and the package manager is simply the piece of software that you use to install everything else. You have to accept some more license agreements. You uninstall the package manager, log into your account, and then you can access your you can access the driver stations.
Okay. So Marshall, I could share you the link to the Java docs right now. And then if you wanted to go over, I could describe what that page is.
Sure. Okay.
All right. So right here, I know I've used this page a lot. If you're ever stuck or need inspiration kind of, or going into any class, this is where you can kind of see or go down a rabbit hole, I guess, of all the different classes and ways to use them. So if you click on one of them, Marshall, it'll kind of show you where you'll end up.
And this is the one I lost my head about, trajectories.
All right.
I've only used this in terms of just trying to get an understanding of the things you currently work with, but you're definitely right that if you want to search for a solution, you can try and find it on here. There are equivalent example pages on the WPILib GitHub, and there are equivalent Java docs for many of the different vendors, such as Rev Robotics, Cross the Road Electronics. They all have their own set of Java doc pages.
All right, I can put the Java docs into the YouTube chat right now.
Please do. How many questions do we have?
I don't see any questions yet. Let me refresh. I don't see any, but so yeah, please, if you have any questions about FRC programming at all, put those into the chat and we'd be happy to go over that.
In the meantime, I'll show you how you can work on installing WPILibx code in more depth. So on the official GitHub of WPILib, as well as showing you some examples and providing information about the latest releases, whether it be for your Romy or for the latest version of WPILibx code, you can get both the examples for their libraries, and you can also get some values about how to install software supported and developed by the WPILib team. So after you find the latest version, you can again mount it, and it should show. You should have a desktop icon show up in the background. The WPILib installer looks nice; it's polished, and you can also, in order to access it, you go through the process of installing it. It's very similar to installing any software, really. They walk you through it.
So we can also go over training programmers. I know we're getting a lot of rookies lately, and even though there isn't much to do since they don't have much knowledge about the robot, they can do things such as helping out with just little classes or bug fixing. We haven't been able to fully get them into that yet, but also getting all the software installed on their laptops and kind of showing them all of these resources is great for getting them into this.
The process our team normally takes to getting rookie programmers up to speed is so the main way we get the programmers up to speed is we first walk them through Java, and that'll be in the combination of direct tutoring and putting them through courses and programs that teach Java. And then after that, you can start to get them installing some of the software, getting them to clone the repository of the team. And then once they're able to both read, update, and modify our team source, we can start talking to them about how they might modify their own classes, start creating classes of their own, start working on some of the code for the robot. And then after that, once you understand the basics, you can and understand wherever you want to focus on. Like some people focus on computer vision, I focus on trajectories. You can start diving into the docs that Brendan put and I was showing you earlier and begin working with those. Another thing I'd like to encourage in any rookie programmer is to look at the examples that other teams have made, whether that be consulting Chief Delphi to see people who've encountered the same problems that you have, whether that be checking on the GitHub pages of other teams or asking the questions on Chief Delphi yourself. And the thing about Chief Delphi is a lot of the time their developers themselves will be able to help you with your questions.
Yeah, and also a big help on our team is that we have little robots like the Romy, and we have an FTC robot. Those are a lot simpler to get into, and especially when we're working on an FRC robot, we don't want to take up any of the rookies' times, so we can have them work on an FTC robot or a Romy, and that'll be a good way to sort of introduce them to this programming. And it's a lot more simple when you don't also have to work simultaneously with any mechanical issues. So I would encourage having them also work on finished robots just to get them started on programming. And also little things like getting the Spark Maxes working, or like installing software on the RoboRio are all things that we have to go through eventually. So teaching them that would also be very useful.
Okay, another thing that might be useful for anyone who's starting programming to understand is just to understand what errors they may encounter. One of the primary errors, as a matter of fact, is the null pointer exception. The null pointer exception means that you are trying to reference a variable that either has been initialized or doesn't exist at all. It is difficult to figure out the origin of, but traditionally, if your code deploys to the robot just fine, your code runs to the robot just fine, you're deployed to the robot just fine, and it isn't working for some reason, and in fact, this has become something that most programmers become familiar with in their first year of programming, is the robots should not quit, but yours did, the error message that it gives you. And that error message means that you have been trying to reference a variable that doesn't exist, among other things. Another mistake, which is much more abstract, is trying to read the documentation yourself and not trying to consult others or Chief Delphi or the work of others beforehand.
Yeah, but basically walking through everything with them, showing them any errors that arise, figuring out how to react to an error message, what and what not to do are all great things. What about some common rookie mistakes, maybe? Let's see. I say one thing would be, do you have any common newbie mistakes, Marshall?
I was sort of talking about the null pointer exception, which is the most common Java error, but the most common rookie mistake is, frankly, not connecting to the robot. That happens a lot of the time. There's also the issue of you're connected to the robot and you had some of your vendor libraries require online installation. So, for example, Driver Robotics has online and offline libraries that you can either access. So online libraries are, you tell WPILib the URL to pull the code from, and then it pulls the code from that URL. However, if you have a wireless connection to the robot and a wireless connection to the internet, you can only choose one at a time. So you have to build your code individually and pull it from the internet. And then you have to compile it and then push that out to the robot. You can encounter that frequently.
Yeah, and one thing that I encountered was the Windows firewall on, if a rookie has a Windows laptop, which they should if they want to program. I think the default setting is to have a firewall, and since the robot actually has a private network, and when that rookie connects to it, it's not automatically going to trust it or send any data to the robot because it has the firewall up. So I always like to check if the firewall is up when connecting to our robot's internet, or not internet, our robot's Wi-Fi, and then going ahead and deploying the code and then running it on the driver station.
Something that is less of a mistake and more of a not understanding of some of the some of the best practices of FRC is the improper use or the non-use of source control. So the de facto standard of using source control in FRC programming is to use Git, which you can either host your Git page on GitLab, GitHub, or some other repository hosting service. And after you have the GitHub repository set up, you've cloned that repository, it's not much use unless you actually make commits and pull code from it. Because something I've experienced and something I've seen others experience is when they have a Git repository, but everyone is working on their code at different times, and everyone is failing to commit and push their changes to the cloud at the end, pushing it to the repository. And so by the end of the season, when someone wants to get someone else's code, they both have incompatible versions, neither of which are standard with the latest version on the cloud. And so Git doesn't understand which one to prioritize over the other. And it will force you to spend up to an hour trying to prioritize the two.
Yeah. So definitely always communicate when you're using version control, because it's kind of hard sometimes to tell when your teammate is trying to do one thing if they never tell you. And then when you're writing your code, maybe if you haven't pulled or something like that, it might just erase it or not use it altogether. And then it's just a waste of their time programming. So I'd also go back to making pseudocode and a flowchart that everyone agrees on, and then programming towards that. I think that makes writing out and using version control a lot easier if you all know where you want to be, and then communicate also anything that you add or new ideas.
Okay, and the final thing I'd like to weave on is some people ask questions about how they're going to edit the source and how they're going to deploy the code to the robot. And you typically do that through an IDE. In fact, you almost always do it through an IDE because IDEs are intuitive ways to determine whether or not your code has any errors before you have to compile it and then it gives you errors. It has dynamic checking of whether or not your code has some syntax errors, which is useful. There are many different ones. You can basically use any IDE for editing the source, but there are only a select few IDEs that you can use to deploy the robot to the code directly. One of those is VS Code. I've heard that the robot dolphins use is IntelliJ. So you can use any IDE to edit the code, and you can use either an external source. I believe there's one of the game pools allows for you to deploy code to the robot, or you could do it intuitively within your IDE if it supports that. We're going to close this meeting. We're going to close this talk soon, but the final advice I'd leave to you is to always check Chief Delphi if you're encountering a problem, or check with your mentor or veteran students. Try to write your code to be as intuitive as possible. Don't always prioritize efficiency because, trust me, efficient code is not the standard. Is not the goal. The goal is to have code that is readable by yourself in a few weeks and readable by those around you. And make frequent commits, frequent pushes, frequent pulls from your repository. And other than that, thank you all for watching the Java programming workshop.
Hello and welcome back, everyone. We now have a wonderful presentation by Taylor from Team Super Nerds on state machine autonomous for command-based robots. So Taylor, take it away.
Hi, everyone. Thank you for coming to my presentation today. So before we get started, I just want to tell you guys a little bit about myself. So I'm actually Team 3255's head coach. I was an alumni on the team, student on the team for 3 years. I started mentoring in 2017. I'm their lead software mentor, and I now work as a cyber software developer at a Fortune 500 energy company. So what is a state machine? So we're going to be going over the basics on what state machines are, in case you haven't heard of it before. So first off, what is a state machine? So the technical definition is it's an abstract model to outline sequential logic So what does that really mean? You can think of it as a map of choices that are dependent on previous choices. So a state is essentially represents a condition or a set of conditions. If a condition or state changes, it results in a transition to the next state. So a really simple state machine example is actually a traffic light. So if a traffic lights, the colors are the states. So in this example, this is a state machine diagram. You can actually see the layout of how the state machine functions. So after about 60 seconds, or after 60 seconds, green transitions to yellow. After an additional 60 seconds, yellow goes to red. After 60 more seconds, red goes to green. And then take important note that red can't actually go directly to yellow and green can't go directly to red because, that's not how it's outlined in the state diagram. So this function won't actually work that way. So it's only exactly what you see there. So that was a pretty simple one. Now we can talk about a little more complex state machine example using everyone's favorite plumber. So Mario is actually a good example of a state machine. When they developed Mario, they probably used the state machine diagram. So, one state can actually transition to several other states depending on the conditions. So in this case, Mario's different forms are the states and the items are the conditions for transitioning to the next state. So normal Mario here has 3 different states he can transition to. He has Super Mario, Fire Mario, and Cape Mario. And then the other states transition to each other depending on what item he collects. So regular Mario can go to Super Mario with a mushroom, and Super Mario can go to Fire Mario with a fire flower, or he can go to Cape Mario with a feather. And then basic Mario can go directly to Cape Mario if he collects a feather. And that's pretty much how you read one of these more complex state diagrams. So a state diagram is really good because it can show some kind of complex logic in a pretty intuitive way. And so this diagram maps all the different transitions that Mario can actually make. And he can't do anything outside of this logic. So why use a state machine? Why should you care? So state machines are really reliable and they're very intelligent. So the code does a lot of the thinking for you and allows you to approach the programming from a more high level or abstract perspective. And so you can think of the code more as step-by-step logic when you're writing it. So now I'm going to go over our state machine autonomous for our 2020 robot. So this is the Super Nerds autonomous robot in action. And here's a quick video from us actually at Del Mar Regional in 2020. And if this video gets a little fuzzy or weird for you, the link for this will actually be in the chat for you to rewatch or look at real quick. Okay, so you're probably wondering now, state machines sound really cool. So how do you implement a state machine? So the number one step for implementing state machine in your code is before you start doing any programming, you want to list out all the states that you're going to be using. So in our case, our WPILib commands that our robot's going to be running. Second step is we want to identify, what are the transitions or the transition conditions for moving from one state to another. And we want to make sure we also include any outside inputs that might be a condition. Next, we want to create a state diagram. So we want to create a diagram of the different states and transitions, similar to what we saw with the Mario and traffic light example. And we want to make sure in this diagram that we show how the completion of one command leads to the next. So a little bit of background on our specific robot and using additional inputs. So my team actually has a custom USB switchboard that we use for our autonomous program. We use it as an additional input. So the switchboard that we have is just a basic Arduino program to act as if it was like a USB controller, like an Xbox controller, and then we just plug a bunch of switches into it. But the switchboard is just seen as any other controller, exactly as, similar to like what the drivers use when they're driving the robot. But instead of momentary switches or push button switches, like on an Xbox controller, press state, we use a toggle or flip switch, which stays in their position once we flip it. And so, funny enough, joystick inputs are actually read during autonomous. That is part of the reason why during the autonomous period, they actually tell everyone to put their controllers down, because the robot's actually still reading what the joysticks are saying, even during the autonomous period. And you can actually read that in your code, just like any other joystick. So for our case, we're using the buttons as additional inputs. So you can kind of think of them as sensor feedback, similar to limit switches on a robot, but instead of being on the robot, they're through the driver station and transmitted over wireless. And so some of our conditions in our state machine are going to actually check if a button is switched up or switched on to determine what state to transition to next. So here's just a basic diagram going over our switchboard design, just to give you a better idea of what it would look like on the in real life. So you can see this is our driver station laptop. Just the switchboard controller is just an Arduino with off-the-shelf switches, and it's programmed to act as a controller. It's plugs over USB and USB controllers. Nothing really special about it, but it allows us to do some power stuff. Okay, so the next part that we want to do is, we want to identify the states. So for our 2020 autonomous, we had 10 different states or commands that the robot actually functions or does during its autonomous. We have 1 spin ball collector state, 3 turret alignment states. Just for reference, one of them is encoder-based and the other is vision-based. That's not too important for the state machine, but just for full transparency. Then we have the 3 shoot 3 ball states. And then we have 3 robot drive states. So with all that said, now we can actually draw up what our state diagram is and what we want it to look like. What state do we want to go to from where? So this is our team's state machine diagram for our robot. So I'll kind of go over step by step what it's doing. So this is actually color coded. So the pink is for any spinning of the ball collector. Green is for any alignment. Yellow is for any shooting commands. Blue is for any driving commands. So that way it makes it a little bit easier to read. So to read the state machine diagram, you start here at this initial state. What this is going to do on the field is it's going to spin the ball collector. In our code, this command is actually called collect spin. So when we look at the code later, that's what it will be called in the code. And this little S0 here means that this is state 0. And this is just a common nomenclature used when you're writing state machine diagrams and working with state machines. From the initial state, after spin ball collector finishes, it'll automatically transition to encoder aligned turret. From there, we actually have our first choice. So this is where we show the real power of state machines. So if switch 2 on our switchboard is flipped in the on position, then we will transition to shoot 3 balls. If switch 3 is flipped on, then we will transition directly to drive backwards pickup balls, and we'll skip over shoot 3 balls. Now, an important thing to note on how this is implemented, switch 2 actually takes precedence over switch 3. So what that means is if we have both switch 2 and switch 3 in the on position, at this point in time, it's going to read switch number 2. That's going to take the higher priority. So it's just going to ignore whatever other ones are on. It's only going to listen to switch 2. So then if we're at the shoot 3 balls state, we're going to move over to drive backwards, pick up 3 balls if switch 3 is on. After that one completes, we're going to automatically transition to drive forward. Then we have another choice. If switch 4 is on, we transition to vision aligned turret. And then if we have switch 5, we're going to drive to the rendezvous zone and pick up balls. And again, switch 4 is going to take precedence over switch 5 in the case if they're both switched on. From the vision aligned turret, this one's a little bit different. So instead of looking at a switch, it's going to say, okay, is the vision alignment actually successful? Did we find a target? As some of you may know, Del Mar Regional is actually an outdoor competition. So we have a lot of different influences from the sunlight, and it can affect what our vision program is able to see. So we want to make sure before we start shooting our precious power cells that we collected, before we shoot them just willy-nilly, we want to make sure we will actually likely make the target and we're not just facing in the stands about to shoot the audience or anything. So we've programmed into our code to return back whether the vision was aligned successful. And if it was, then you shoot the 3 balls. If it's not, and switch 5 is enabled, we'll just go drive to the rendezvous zone. From there, if switch 6 is enabled, go ahead and do vision aligned turret. And again, if the alignment is successful and we have our target, go ahead and shoot 3 balls, then end our autonomous. And now an important thing to note is if any of these states at any of these positions, so, for example, here, if neither switch 2 nor 3 are on, autonomous is just going to end. So if no conditions are met, autonomous will just end early. So I'm going to show that same video I showed a little bit earlier, but this one is going to have a little bit of labels on it to show you when it's actually doing what. And I just want to highlight what in this video specifically the robot was doing. So for this video, in this case for this match, we had switches 2, 3, and 4 in the on position. So in our state machine diagram, we can now read our state machine diagram and know exactly what our robot's going to do. So we're going to spin the ball collector, line the turret, shoot 3 balls, drive backwards, drive forwards, align the turret again, and if it aligns successfully, shoot 3 more balls. So this is our autonomous video again, same one as before, but with the labels. And if your video gets a little fuzzy from the Zoom call or the YouTube stream, the link will actually be in the chat. So first we spin the collector, then we vision align or encoder align the turret, shoot 3 balls. Then we start driving backwards and we pick up additional balls. Now we're in state 4, we drive forwards again, vision align the turret. That completes, shoot 3 more balls. And then our autonomous is over. So that's pretty cool. So how do you actually, program a state machine autonomous code? What does our code look like? So for this section, we're going to go over some assumptions. When I talk about in this section, we're going to assume that you know some basics on FRC Java programming or just FRC programming, and that you have some base level familiarity with WPI Lab command-based programming, because that's what my team uses and how our code is laid out. And then it's going to assume that you have some familiarity with just basic autonomous programming. You know, you've made the robot at least drive forward or something like that in autonomous. Okay, so programming a state machine, the first thing we want to do is we want to define our states. Then in our code, we're going to create a variable to hold the current state. Then we'll set the initial state, and then we start writing the conditionals to compute when we should change from one state to another. So we're going to do all of this in a single autonomous file. And so just for reference, you know, our autonomous command file is just a standard WPI lib command. There's nothing special about it. It has all the standard methods: initialize, execute, end and is finished. And so there's nothing special. It's just a basic WPI lib command. Some of you may not know this, but is finished is actually called repeatedly to check, you know, repeatedly if the command is finished running. And that's where we're going to hold and program all of our state logic. All the transition changes will be programmed in that part of the code. So here's a little bit in depth, a screenshot of our code. This is at the very top of the code when we first create the class. So first thing we're going to do is here we've defined the 10 different states that we actually identified earlier. And we're also going to create a variable called current command state to store the current variable or the current state. So you can see here, these are the states that we went over earlier and that you guys saw in our state machine diagram. We have a line 1, that's the encoder line turret. A line 2, that's the vision line turret. 3 is also vision aligned turret. Shoot 1, that's going to shoot 3 balls in real life. Shoot 2 is also going to shoot 3 balls. Shoot 3 is going to shoot 3 balls. And then down here we have drive 1. In real life, that's going to do the reverse driving the robot, where it will pick up additional balls. Drive 2, that's just going to drive the robot back forward. Drive 3 is going to drive to the rendezvous zone. And collect spin is going to spin the ball collector. And then we have this placeholder variable called current command, and that's going to store what our current command or our current state is. So now the first thing we do is we set collect spin as our current command in the initialize method. So as you remember, this is just a basic WPI lib command, which means it has an initialize method. This is called at the very start of the command. And so this is where we're going to set what the current command or the initial command is. So we're going to set current command to collect spin. And since this is the state we start off with, this is going to be defined as our initial state. This will be the first command that runs, our starting point. Next up, we're going to start computing the transitions with our different conditionals. So the current command and the switchboard buttons are going to be checked to determine what the next state or the next command should be. So here you can see this is an is finished. If the current command is collect spin, we're going to switch the command to a line 1. If it's not, else if current command is a line 1, check to see if the button 2 or switch 2 is switched on. Then we're going to switch our command to shoot 1. Else, if button 3 is on or switched on, we're going to switch the command to drive 1. And then if none of the conditions are met, autonomous will end. And you may see you see here we've written switch command. All that's really doing is making sure the current command ends, setting the current command to whatever we passed in this value. So like drive 1 would be passed in, and initializing it to make sure everything is set up to run it. So just seeing all the code at once can be a little bit confusing. So we're going to break it down a little bit further and show the code and the diagram actually side by side. So for the initial state, the spin ball collector, it says if current command is collect spin, switch the command to a line 1. So you can see spin ball collector will transition to a line 1 as soon as the command ends. So this one's a little bit more complicated. This one involves our switchboard. In our case, we had switch 2 toggled on for the video. So if the current command is in a line 1 and the button 2 is switched on, we're going to switch our command to shoot 1, which will do the shoot 3 balls. Else, we check if button 3 is on, and if button 3 is on, if switch 3 is in the on position, we're going to switch our command just directly to drive 1. Then after that, if the current command is shoot 1, check and make sure that switch 3 is on. So this is button 3. See if it's in the on position, and then switch our command to drive 1. And that's pretty much it. That's the basics on stateful autonomous programming. So just a little bit of review. We went over what a state machine is. We discussed the benefits of using a state machine model, and then we use a state machine diagram to implement our autonomous code. So I highly recommend that everyone give it a try. If you're interested in drawing state machine diagrams or doing that, a great resource for drawing these state machine diagrams is actually this website I found back when I was in college having to do this. The link for this will be in the chat. And then I also recommend that you take a look at our 2020 autonomous code, where you can kind of see in a little bit more detail what all that code looks like. So with that, any questions? Let's see. So I see one question in the chat. Are switches the main way to change from state to state? Switches are typically the main way that our team switches from state to state. But like I mentioned earlier, and in this vision alignment, we actually programmed our different commands to return back whether they succeeded or they failed. So for a more complex command, something like vision, a vision alignment, we want to make sure to move on to the next state in our autonomous to continue on. We might forcefully or set a timeout for our vision code or vision alignment. While the turret is turning, trying to find the vision target, it's either going to, 1, find the actual target, and that's a success, or it will time out, which means, it didn't find the target in the allotted amount of time. And that one we're going to consider a failure. And we still want the command to actually finish in either state so that we can, run our logic to go on to the next step. So we don't just want to run the logic infinitely for aligning the turret. So our vision aligned turret will actually say, hey, we succeeded. And we actually use that as a condition in our code to see if you succeed, go on to the next step. So another question in the chat is, what other versions are there besides state machine diagrams? Is there a specific reason you think state machine is better than those? So a state machine diagram, that's a pretty common one used in the field a lot for different automation. And so we typically chose the state machine diagram because we have a lot of different choices to branch off of. Versus, some of them use different flowcharts. Those are more for conditions going down in like code logic, and So another different one that you could use is, a flow chart. But typically for automation, a lot of people use state machine diagrams, and we find the kind of flow from one state to another with these conditions to make it a little bit more clear and easier to read and understand, at least in my opinion. So that's why our team uses that versus something like a flow chart. Another question is this the first year your team used state machine diagrams? Yeah, so this year was actually the first year our team used state machine diagrams to kind of represent our code. And it makes it a lot easier to actually figure out what you want to program. Because, in real life, you think, okay, I want the robot to do this, then go to this step, then go to this step. But, the reason that our team wanted to make a more complex software or autonomous program is because what if your partner or alliance partner, what if they have an autonomous that will cross over in front of yours? Okay, well, we don't want to have to program our robot or, reprogram our robot to take that part where we're going to crash into each other while we're in the queue to go out onto the field, because that could lead to issues. We might forget something and then our autonomous doesn't work at all. Instead, we used our state machine diagram to, draw out all the different scenarios and map them to switches. So that way, we can still do part of our autonomous or a different route for our autonomous without having to, change any of the code. And the diagram just makes it really easy to see all that. Otherwise, it's just kind of in someone's head or written down in text. And that's a little more confusing than a visual representation. Okay. Any more questions from anybody? Okay. No more questions. So with that, I want to thank you all for coming to my presentation. Thank you very much.